Hello friends, welcome to Multiverse YouTube channel. It's a one-stop solution for Gate ESE, SSC JE, all AJE PSU exams, and for college-going students who, for semester exams also. So in the previous class we have discussed totally irreversible process. What do you mean by irreversible process and their causes of irreversibility? Cyclic process and some characteristics of properties. Now we will be starting with universal gas constant. Suppose I am taking a piston cylinder arrangement which is filled with a gas and the gas have some volume pressure and some temperature. Okay, and some temperature, and this is a gas. Here, what do you mean by universal gas constant? I will be representing universal gas constant as R. As R bar. Okay. Here, universal gas constant means suppose a number of moles is equal to mass small m upon molar mass. For number of moles, uh, the SI unit will be, here mass means kg and molar mass means kg per kilomole. If we cancel this kg and kg, then we will get the SI unit as kilomole. Can I measure this volume, this pressure, and this temperature? Yes, we can measure it. If I take temperature as constant, and I plot the values, I will get some values. And I am taking this axis as pressure axis and this axis has PV by NT. Suppose when the temperature is constant, I will get the some values of volume and some values of pressure, and when I substitute here, I will get some values, and I will be plotting those values in this graph. Like this. And some expansion is taking place. Suppose the temperature is T2 and the temperature is constant when the expansion takes place, and I am getting some values of volume and pressure, and I am substituting those values of volume and pressure in PV by NT. I will get some result, and I will be plotting those results here on this graph. Similarly, again some expansion is taking place. The temperature is T3 and the temperature is constant, and you can observe that there will be some change in volume and pressure, and I will substitute those values in PV by NT, and I will get some result, and those values I am going to substitute in this graph. Okay, and I will be joining these values. I will draw it clearly so that you people can understand. I am plotting those values when the temperature T1 is constant and after expansion the gas of the temperature becomes T2 and the temperature is constant, we will get some values of PV by NT. Okay, and again some expansion is taking place. The temperature becomes T3 the values of PV by NT changes. Okay, and this, suppose this gas is oxygen and I am doing an experiment for oxygen. Okay, here as usual I can tell that the pressure tends to 0 and this value is some C1. Okay, again similarly I am doing an experiment for nitrogen gas. Again I will get the same result as I told you before. Okay, and I will be joining these values. and this is the height C2. If I define C1 as the limit when the pressure tends to 0 PV upon NT, and similarly for nitrogen gas the value of C2 is limit tends when the pressure tends to 0 PV by NT. With the help of the scale, we measured the values of when the C1 and C2 are equal. I am getting the value of C1 and C2 has 8.314 kilojoule per kilomole Kelvin. Here what you can observe is if you do an experiment for all the gases, you will get a constant value which is 8.314 kilojoule per kilomole Kelvin, and this constant value is known as universal gas constant. Okay, so suppose as I told you that the value C1 is equal to C1 or C2 is equal to limit as the pressure tends to 0 PV by NT, that is equal to universal gas constant limit pressure tends to 0 PV by NT. Again I can write it as the value of universal gas constant will be 8.314 kilojoule kilomole Kelvin. Again I can write it as 8.314 joule mole Kelvin. Here if I cancel kg, if I multiply with 10 cube, then the value of R bar will be 8314 joule kilomole Kelvin. I think you guys have understood. Now moving further, compressibility factor. I can represent compressibility factor as Z. Now, mathematically, I can define compressibility factor as Z is equal to PV by NT upon R bar, or else I can write it as PV by N R bar T. This is the basic definition of compressibility chart. Okay, as I told you, the graph of universal gas constant, how the gas behaves when the value is PV by NT. Okay, here when I drew this graph, what will be the, and this is the pressure axis. Here the pressure tends to 0 as usual, and this is PV by NT. What will be the value of compressibility factor on this line? And similarly, what will be the value of compressibility factor on this line? Here, this is the value of PV by NT value. This is the PV by NT value, and this is, as I told you, that this distance is r bar. As I told you that this is the value of PV by NT and this is the value of R bar. This is the value of R bar. Means the value of compressibility factor here will be Z greater than equal to 1. And here similarly you can see, observe that this is the value of PV by NT and this is the value of R bar. Okay, so here the value of Z will be less than 1 and as usual you can say that here the value of Z will be equal to 1. Okay, at when pressure tends to 0, the value of compressibility factor will be 1. Whenever you are comparing some temperature and pressure in the atmosphere, whether the temperature is high or low, whether the pressure is high or low, how we can conclude that the pressure and temperature are high or low? In the atmosphere, suppose there is a gas, how we can conclude that the temperature is high or low, or whether or else the pressure is high or low? Here comes the another topic called critical point. The temperature or pressure of a substance is high or low with respect to its critical point with respect to its critical point. In the bracket you can write it as critical temperature and critical pressure. If I explain you this critical point in graph, Suppose I am taking this axis as temperature axis, and this is I am taking as entropy axis. I will be explaining this critical point in brief in properties of pure substances. Okay, here I am giving an overview of critical point. Suppose I am drawing uh, taking a dome. This is the saturated liquid curve, and this is saturated vapor curve. This is the liquid phase, this is liquid plus vapor phase, and this is the vapor phase. I am taking some isobars. Okay, here the first isobar, the pressure is constant, and for the second isobar the pressure P2 is constant, and for the third isobar the pressure P3 is constant. As here you can observe that there is a trend following here with respect to pressure, is that the pressure is increasing, and the final isobar is where here the pressure is the critical pressure, which is constant. The this point we can conclude as the critical point. Then only you can tell whether the temperature is high or low, or whether the pressure is high or low. With this reference point only you can tell whether the pressure is high or low, or the temperature is high or low. This is known as critical point. For water, the critical pressure is 221 bar, and for temperature, and For water, the critical temperature is 374 degree Celsius. For nitrogen, the critical temperature is minus 147 degrees Celsius. Okay. Now moving further, what do you mean by a reduced property? Suppose I'm taking some property A, the reduced property A is equal to A by critical property A. With the help of this, I can write for the pressure and temperature. The reduced property PR is equal to P by PC. And for temperature, the reduced temperature TR is equal to T by TC. Okay. Here, reduced property at a given state is the value of property at that state divided by the value of property at critical point. I have wrote the definition as I explain here. Okay. At some state, some property A I have took, and there is a value of the property sum that is divided by the property called critical point of that property. Okay. Now at some state the pressure is less than critical pressure, means the reduced pressure will be less than 1. Similarly, if the pressure is greater than critical pressure, the reduced pressure will be greater than 1. If the pressure is equal to critical pressure, what will happen is the reduced pressure is equal to 1. Again, at some state, if the temperature is less than Tc, means critical temperature, the reduced temperature will be less than 1. And if the temperature is greater than critical temperature, the reduced temperature will be greater than 1. If the temperature is equal to critical temperature, then the reduced temperature will be equal to 1. From this above all equations, what I can conclude is that at critical point, reduced pressure is equal to 1 and the reduced temperature is equal to 1. Okay, here there is a small conclusion. Reduced property is dimensionless quantity. Okay, guys. And at critical point, its value is unity 1. Guys, my stylus is charging have been completed, so I will continue the class in another session. Please like the session, share to your classmates who are preparing for these following exams and for semester exams also, and for knowledge purpose also. And for PDF, please download Telegram app and search Multiverse exams.